Can you view the screen?
Yes, sir.
All right. So if you have any question, please you can ask now.
Sir, is there tutorial today?
There will be no tutorial, so there will be a little bit extra class till I prove the theorem. So tutorial will be from the next time onward. But I have uploaded an assignment which you need to submit first. After that, tutor is going to solve. All right?
Yeah.
Yeah. So that is it. First, you need to submit. After that, tutor going to upload solution possibly or explain the solutions in the tutorial. Yeah. Any other question?
Sir, I have a question regarding point-wise convergence.
Yeah. Sure.
So, if we have a domain in which we define the sequence of functions, even
Yes.
if at one point in the domain, if the function is divergent, so
Yeah.
we cannot call it a point. It doesn't converge pointwise, right?
Right. Right. So at
Yes.
every point, when you evaluate at a fixed point, and you get a corresponding sequence, that sequence should converge for every point.
So if I show for one particular point in the domain, it doesn't converge, it diverges. Then it's no longer a pointwise
Yeah,
convergence
then
sequence.
it's no longer a pointwise convergence sequence.
Yes. Thank you.
Okay. Any other question?
Sir, by when do we have to submit the assignment? Because it reads deadline 24th August on the PDF.
Oh, really? 24th August? No, it's actually next Sunday.
Okay, so you meant 24th Jan.
Yeah, yeah, yeah.
Okay,
So
okay.
I just missed that one because I was copying from another earlier assignment, taking earlier assignment and changing things. So that's why I missed. Yeah, 24th Jan. So I'll upload. So portal is not open yet. It seems right. So I didn't open yet. So I'll open the portal. There you need to submit all these assignments and you will learn only. Okay. Any other question?
Sir, I had a question regarding the way the questions are phrased in the assignment. Like for a question, it is given that show either it is uniformly convergent or pointwise convergent. If the function is not specified, do we have to somehow check that it is not convergent to any function or something like that?
No. First of all, see the thing is first thing you should note is the following that uniform convergence implies pointwise convergence. Somebody noted it that day itself, right? So you make note this one. So therefore, you must have a limit first of all. If there is no limit, then it is not convergence, not pointwise convergent, not uniform convergent. Also, all right?
Yes, sir.
Sir,
Yeah,
yeah, can we use this because the first question in the assignment, the parts, the 10 parts of the first question, I guess,
yeah.
are all a function, and then it is asked show that find whether it's pointwise convergence and find whether it's uniform convergence. Can we use this theorem there? If something is uniformly convergent, then we just keep it there that if it's uniformly convergent, it must be pointwise as well.
Yeah, yeah, yeah. This one is automatic by the definition. It's not actually a theorem. It's just an observation. You look at the definition, you'll get it. Yeah,
Okay,
this
sir.
one you can use.
Okay, okay.
So first thing to check is whether pointwise limit exists. So once you get a limit, after that you can check whether the convergence is uniform or not. Right? Does that clear your doubt?
Yes, sir. Also, if we just tweak things around a little bit, we can make another observation that if it is not pointwise convergence, it is not uniformly convergent.
True.
So we
Yeah.
can use small things like this, right?
Of course. Yeah.
Okay,
So
sir.
this
Okay, sir.
implication is, I mean, negation of the. This implication is itself not pointwise convergent. It implies not uniform. So
I
so
actually started doing things. I started doing the assignment a little, and I was showing things again, and I showed the same thing again and again. So yeah, I
no,
have
no,
to
no.
change it.
If it does not pointwise convergence, it does not converge uniformly. Don't worry. So
Okay.
first you need to check pointwise. After that, after it converges pointwise, then only you check whether it converges uniform or not.
No, okay, sir. Thank you, sir.
Okay. Any other question?
If we use some other theorem, is it enough to just state and prove it?
Is it enough to use what theorem?
For example, there's a theorem that if a sequence of continuous functions converges to a limit, then that function will also be continuous.
It is not true. Convergence has to be uniform. We'll prove that one
Sorry,
today.
uniformly continuous, yes.
Right. So, but yeah, I'll suggest you don't use these theorems. Try to use the definition. And why I'm doing that? Because if you if you try to avoid epsilon n, and then it will be difficult. Analysis will always be difficult for you later on. So don't try to avoid this epsilon n. Just face it for the first time or time being. These few questions, and of course, I mean, in most of the cases, you will be able to find with epsilon n itself from definition itself, and that way you will know better what actually uniform convergence means. And if you use the theorem, you will say that it doesn't converge because of that theorem. Well, that theorem we are going to prove. So, but I will like without using that theorem.
Okay.
Yeah. Yeah. Any other
Sir.
question?
Yes, sir.
Yes.
Sir, last semester we learned about uniform continuity, and this semester we're learning about uniform convergence. Is there any relation between these two? I mean, I just thought there may be some relation for the name.
Right. So the point is, the thing is, uh, the name uniform, convergence and continuity, two distinct concepts, right? But the uniform, they match in the uniform sense, right? So what is the definition of uniform continuity?
That
So,
for any epsilon, if x to the power n, I mean, if fx minus if y is less than, uh, if you can find a delta such that fx minus fy is less than delta for all x minus y less than epsilon, so we say it's uniformly continuous.
no, no, you are wrong again. So the definitions are most important object in analysis, all right? So first of all, the definition, continuity definition, how it comes when x and y are small, fx and fy should be small. It would be of this form, right? So for every epsilon, there exists a delta such that mod of x minus y less than delta implies mod of fx minus fy less than epsilon.
Oh, okay. Oh, I see.
All right.
Yeah.
So the definitions are very important. If you forget definitions, you are gone.
Yes, sir. Sorry, sir.
But definition doesn't come from sky. It has interpretation. It has certain background from which it comes. All right. So uniform means that epsilon you have chosen, that delta you have chosen does not depend on x. And uniform convergence here, the n you have chosen, that does not depend on x. So if you look carefully to definition, this is the same between these two. This is the catch.
Okay, sir. Okay, sir.
So
Got
it
it.
is just the uniformness. It is nothing about continuity or continuity and convergence are two different things. All right. Just the uniform part is this one, that it does not depend on the point x. The delta you got there, and n, the natural number you got here.
Okay, sir. Thank
All
you, sir.
right. Any other
Thank you.
question? Any other question? So since there is no other question, so we'll start. Today is 19th. Right. So have you heard about Cauchy sequence?
Yes, sir.
So what is Cauchy sequence?
Uh,
Sorry,
Far
sir, my mic was off. So basically, sir, in a matrix space, a sequence in that metric space is called Cauchy sequence. If for every epsilon greater than zero, that is, we have a n that belongs to natural numbers, such that d of alpha m comma alpha n is less than epsilon for all such n and m that are greater than or equal to n.
Okay. So you guys have studied metric spaces? Huh?
So yeah,
Yes, sir.
sir told the definition. Yeah.
Okay. So if somebody is confused about metric spaces, consider R and taking the metric as the distance, usual distance. The metric space, the thinking about metric space is not that important at this point. But if you want to think about more than just R, you can think about R2 and R3. So R2 and R3 you have done coordinate geometry in the school, right? So you know the distance. That is the metric there. And you can do this all these things together there. For example, R2. So R2 is the distance between 2 points you already know from coordinate geometry. That is the metric there. And you can do all the analysis there also. All right, so I'll talk about Cauchy sequence in the case of real number. Sequence in of real numbers is said to be Cauchy sequence if for every epsilon greater than 0 there exists n, I'll put n naught, such that mod of an minus am less than epsilon for all n m greater than naught. Alright. Now we will take this concept in case of sequence. In case of sequence of functions. Right? So the definition: uniformly Cauchy sequence of functions. A sequence of functions Fn on E, a subset E of R, is said to be uniformly Cauchy if for every epsilon greater than 0 there exists n naught n such that mod of fnx minus fmx less than epsilon for all n greater than n for all mn greater than n naught and for all x in E. This part gives you the uniform. Right, so this n naught again does not depend on this n naught does not depend on point x. Alright? Is the definition clear?
Yes, sir.
Alright. So before going into examples, let us just look at one fact. Just as in real numbers, sequence is Cauchy if and only if it is convergent, right? Is it a true or false statement?
Yes, sir.
True statement. We have similar thing here. Let me put this as a theorem. Sequence functions Fn on E subset of R is uniformly Cauchy if and only if is uniformly convergent. Right? Just the analogous. Whatever happens for the real number, this is happening for the functions also. The sequence of functions on a subset R, subset E of R, is uniformly Cauchy if and only if it is uniformly convergent. Right? So the examples will be uniformly convergent sequences. All right. So if you want to see examples, you need to look at a sequence which converges uniformly. So let's look at a proof of it. This proof is very simple. So first, let us assume, go from this side, assume n converges uniformly. So once it converges uniformly, it should converge to a limit, right? Converges uniformly to a function f. So unfold the definition for every epsilon greater than 0, there exists n naught belongs to n such that mod of fn x minus fx less than epsilon for all n greater than n naught for all x. Right? So now, well, we can do this for epsilon by 2 also. Right? Choose mn bigger than n naught mod of fnx minus fmx is equal to mod of fnx minus fx plus fx minus fmx less or equal to mod of fnx minus fx plus mod fmx minus fx. This is less than epsilon by 2 plus epsilon by 2 for all mn. Bigger than n naught. Already I have chosen this one. And for all x in A. Therefore, Fn is uniformly Cauchy. Is this part clear? You can do this one for epsilon by 2 also, right? You can get, instead of epsilon, you choose epsilon by 2 and there exists n for this epsilon by 2 such that this holds. Alright? Now, once you choose mn greater than n naught, you can have both of them less than epsilon by 2 by this, by 1. By 1. Right? Is this clear?
Yes, sir.
All right. Now other side. Suppose if n is a uniformly Cauchy sequence of functions. Right? We need to show that n is uniformly convergent. Right? Now that requires limit function. Do you understand this? This requires a limit function. The definition of uniform convergence requires a limit f, right? Without that, we have not defined uniform convergence. All right, is it clear that you need a limit?
Yes, sir.
Right. So, do you have a scheme? How do you find a limit? What you are given is n is a uniformly Cauchy sequence.
So, can't we choose any function, which is any function such that the n value is greater than n naught? That fn, we can assign it as some f, right?
That function, that may not be the limit, right?
So, but we know that for all m and n greater than m naught, fn minus fnx minus fmx will be less than m. So, what if we assign that fmx as cf?
Sir,
Yeah, this is true for all n. So which n would you assign? Yeah, anybody else? You are
sir, if this sequence of functions is uniformly Cauchy, then we know that n naught does not depend on x.
true.
Yes, sir, in the previous class, we studied that uniform convergence is when epsilon n naught depends only on epsilon and does not depend on x. So from that, I guess we can conclude it.
No, we need a candidate f. Yeah, the point is, who was speaking about this assigning n?
Sir, Siddharth.
No, that is fine. No, the other one was speaking. I don't see the names here, right? So I'm in the screen.
I'm Niveda.
Oh, Niveda. Okay. So you were
Sir,
speaking about.
oh no, sir, I was just.
If you want to say something, say it clearly.
Oh, I was just. I had a thought if I wanted to say that.
Yeah,
What does
you just say it. Let me clear the comments. Nivida was saying that some n or m greater than whatever n naught can be put as f, right?
Yes,
Right?
sir. Yes, sir. That's what I told.
Right? But if you change the epsilon, then what happens? That then might be living far behind, right? So once you fix an epsilon, then you get an n. All right?
Yes.
Now, if you change the epsilon, let's say epsilon equal to 1 over 100, you fix an m, and choose and you have put it as f, assigned it as f. All right. Now if you choose epsilon to be 1 over million, then your this will not be
Sir,
this attempt will not work.
sir,
Right? Yes.
sir, I'm just guessing. Can we put this limit function as limit n tends to infinity fn x? Because we know that this is well defined. Limit n tends to infinity fn x is well defined since fn is Cauchy. So that's
What?
that's
Say that
the
say that again. Your idea is correct, but yeah, say that again. Why?
limit n tends to infinity.
Uh,
Fn x is defined well defined because fn x is a Cauchy sequence. Can
Fnx
we?
is a Cauchy sequence.
Hmm. So
Yeah.
limit
So
n to infinity fn x is well defined.
how do you what do you mean by well defined?
I mean this limit exists.
This limit of what? Limit of functions?
Yeah, this limit of function exists.
So can we take the point-wise convergence function of this?
Right. So what he was saying? Who was saying last?
So me,
Yeah.
I am Shayon.
Sion. Yeah.
So,
So
sir,
what
the
Sion was saying is actually correct. You fix a point. Now you get a real number, right? A sequence of real number fnx.
Hmm.
Now since fn is Cauchy, fnx is also Cauchy, right?
Hmm.
Cauchy sequence of real number.
Hmm.
What happens to it?
So every Cauchy sequence of real numbers must converge to a point in R because
Right.
it is Cauchy. So
Right.
we define a function fx such that
Right.
if x naught is the point where the sequence fn of x naught converges.
True. Right.
So this
That's
is the function. This is the function that we will use as a limit function in this proof.
right. So this is correct. Yeah. Anybody else? Is this clear? So you fix a point. So we require a limit function. So a candidate. So the candidate is, since fn is Cauchy, the sequence of real number fnx is also Cauchy. Hence convergent. Therefore, we define fx to be limit n tends to infinity fnx. Yeah, whoever was saying the pointwise limit, that is true. But you need to know that pointwise limit exists, and that is the way to go. The Cauchy sequence of real numbers converges. Right? It is not given that pointwise function sequence of function given a sequence of function is pointwise convergent. What is given is the sequence of function is uniformly Cauchy. From there, you need to use the Cauchy property of the sequence of real number fnx. From there, you get the limit. All right. Is this clear? Now we have a candidate. Yeah, is this clear?
Yes, sir.
All right. So next, now you need to show aim is to fn converges to f uniformly. Right? So we need to look at fnx minus fx. Alright? Now what you will do? You have uniformly Cauchy, right? So I should write that definition. Given Fn is uniformly Cauchy. Therefore, so for every epsilon greater than 0, there exists n naught belongs to n such that mod of fnx minus fmx less than, in this case I'll put epsilon by 2 to make letter epsilon. It doesn't matter actually. For all n bigger than n naught, for all x. Alright. Now, so let's call this 2. Now we now look at following fnx minus fx. Now you put fnx minus fmx plus fmx minus here let me change a little bit. Instead of n naught, you put nx. Alright? So this one you put nx. And here you put m. You can choose actually a particular m, which is f of nx plus 1 x plus f of nx plus 1 x minus fx. So for every x, this nx depends on epsilon and x, right? So we put that nx plus 1, the next term of it, because I have chosen greater than. If I have chosen greater than equal to, nx would have been good enough. Now this is less or equal to fnx minus f of nx plus 1 x plus f of nx plus 1 x minus fx. This is less than epsilon by 2 plus epsilon by 2, right? And now this is true for all x in E and for all n bigger than what? We need something, right? Bigger than what? Bigger than this. What is the definition? Oh no, I'm extremely sorry. This is n naught. This is n naught. This is n naught. This does not depend on x. Then what do I get? This, where do I get this nx? Nx is a different thing coming from here. Well, let me Right. So we need to look at this one. This is fine. But before that, we need to do something. We need to get the nx. Right. Since fnx converges to fx for every epsilon greater than 0, there exists nx belongs to n such that nx depending on x and epsilon such that mod of fnx minus fx less than epsilon by 2 for all n greater than nx. Alright. So this is the nx. This is the nx we are using. So here we have chosen this nx plus 1. So n greater than, from here it should be greater than nx and it should be greater than n naught. So n greater than, let me change the color, and n greater than maximum of nx comma n naught. Is this clear? Why do we need maximum?
Sir, I don't understand the Fn converges to F for all for every epsilon greater than 0. I don't understand that aspect, because isn't that what we are supposed to show, that Fn
Oh
x?
no, this we have now this limit, this one, pointers convergence.
Oh, okay. That's
So
from
this
definition.
this is pointwise convergence. So this part is pointwise convergence. Pointwise convergence. And this part is uniformly Cauchy. This part is uniformly Cauchy. So first we have shown that Fn converges pointwise. Since we have a limit, first of all. Next we have to show that it converges uniformly, and that's why we are looking at this. And this one here showing uniform convergence. Is this clear now?
Yes, sir.
Don't you also need nx to be greater than n naught?
Yes, sir.
Yeah,
So just nx plus n naught maybe as the subscript.
Yeah, that's better. That's better. Yeah, thanks. Instead of 1, you just look at x plus n naught. Right. Is this fine?
So how do we have the for all x in E at the end of this?
How?
How do we know that it's for all x in E at the end of this? You have written for all x in E for all n greater than max of nx and naught.
Yeah. So this is what your new n naught is. Right? This is capital N. This thing is capital N. The whole thing. So the definition.
But the capital N suddenly depends on x now, right? Because nx depends on x, and the maximum will then depend on x.
Oh no. Ah. Oh, that is interesting. That is interesting. So we don't need max actually. So
Just n0 is sufficient, I think.
just n0 is sufficient. So yeah. Thanks. Yes, because we have chosen n0 plus n. So this part here in the middle, whatever you do doesn't matter actually. As soon as it will be bigger than n0 and bigger than nx. X and here this part depends. So this depends on x. This depends on x. It will changes for every x. You see the trick? Ultimately, it is true for all x. But in the middle, when you are using triangle inequality, this depends on x. This too depends on x. Depends on x. But ultimately, this thing is true for all x, independent of x. This means here, this term depends on x, but ultimately it is not. It doesn't depend. Yeah, is this clear?
Sir,
Yes.
can you explain why we choose nx plus n not?
Oh, you have two inequalities. This one, you are using two triangle inequality, one of this form, another is of this form. All right, one is of this form, another is of this form. Right. So here this is true for all mn greater than n0, and this is true for all n greater than nx, right? So for this part, whatever you put here, it should be greater than nx, right? And whatever you put here, it should be greater than n0. Now making sum actually makes both of things together.
Okay, sir.
All right. Any other question? So this implies Fn converges to F uniformly. Yes. Yes. Who was saying? Who was saying? Please say that again.
Yes, sir. Sorry, I was thrown out of mute. Can you once again explain me why it does not depend upon X? Because I stopped following after some lines. Sorry.
Yeah. So which line did you stop following after?
That fnx minus fx is equal to fnx minus fnx and not x plus fm, like we are adding and subtracting the term fmx wala. fn
Yeah.
fn and
Next one is triangle inequality. Right?
Yes, sir.
This one
But
is just triangle inequality.
anyways, na fn
Yeah.
f nx plus n not depend upon nx, which depends upon x.
True. But that is independently chosen, right? So this is chosen arbitrarily. Now whatever you can choose here, right? It depends on x, but this can be chosen for every x. Every x you choose one for these things. But ultimately, how does it matter, right? So this nx, this nx is not fixed. Remember, this nx here is not fixed. as x changes, nx also changes. All right?
Yes.
Come here now. So this f nx plus n naught changes as x changes. It's not the same. But what is same is less than epsilon by 2. That is same. So here we are using this one for every x. For every x, there exists an nx. For every epsilon, this is for each x. For every epsilon, there exists an x such that this holds. Right?
Yes.
These nx changes. So this in between, as you change x, this part changes. But whatever you keep in the middle. So for example, you are from one story to other story. I mean, let's say from ground floor to say first floor you want to go, and you don't know whether there is a stair or not, anything. In between, if you, whether you jump, whether you make 2 step, whether you make 3 step, whether you jump it together, doesn't matter. So if you basically you are searching, let's say the story is like you are searching in the ground floor if there is a stair or something, or there is somehow you can go upstairs. So in some cases you see there is quite up. If you can go quite up, then you can jump from there and go to the first floor, and so on. So that one depends on every place you move. That part depends. Somehow somewhere you might get a z1 from where you can go, and this is exactly what we are doing. For every x, you have that nx. That nx plus n naught is greater than n naught, greater than nx. So this inequality follows. Nx plus n naught is greater than nx. Hence this inequality follows. So we can use this inequality here for every x. Nx changes, does not matter. But ultimately this will be less than epsilon by 2. That we can make sure from here. And this part is uniform. This one, as nx plus n naught bigger than n naught, for all x this is true. This part is uniform, does not depend on x. So hence this is epsilon by 2. Does this clear, or it made more confused?
Yes, sir. Yes, it has clear.
Cleared?
Yes, sir.
All right. Yeah, any other question or doubt here? Okay, so it converges uniformly on set E. All right. So you see uniformly Cauchy sequences are the uniform convergence sequence. This is a nice thing. And let's look at the main theorem of this portion. Let Fn be a sequence of continuous functions on E subset of R. You can choose interval if you like, such that Fn converges to a function f uniformly E, then F is also continuous on E. Do you know continuity on any on a subset of real number, or do you need open or closed interval?
We had continuity in the last semester.
Of course you have, but do you know continuity for in arbitrary subset of R?
We had continuity. I think we had continuity on any metric space. I think so.
Oh, anyway, that is good. So let me ask you a question. So what are all continuous functions on natural numbers?
Any function on natural number is continuous.
So is this clear to everybody? Any function will be continuous? Right. So any function will be continuous. And so if you are confused with this arbitrary subset, you consider this subset to be closed interval. Generally, uniform convergence behave very well on compact sets. We'll show that, but before that, let me go. Let us try to understand this one. So in general, pointwise convergence does not give you the limit function to be continuous. What is this theorem says that uniform convergence does give the limit function to be continuous. I'll be extending today a little bit because there will be no tutorial today. And tomorrow also there's a meeting with director with all the faculties of our department. So I'll take a half an hour class too. So that is the reason I'll be extending now a little bit till the proof of this theorem. Yeah, so this statement of the theorem is clear, right, to everybody?
Yes, sir.
All right. So, proof. Let us first write what we need to show. So, for every epsilon, there exists delta greater than 0 such that mod of x minus x naught less than delta implies mod of fx minus fx naught less than epsilon for each x naught in A and for every epsilon f. Right, this is what you need to show. Right? This is what we need to show. So to show continuity, one need to start with this generally. And then use some kind of triangle inequality stuff. We'll use that. All right. Now, how do you know what is given? If n converges to F uniformly on E. So, which means for every epsilon greater than 0, there exists n naught in n such that mod of fn x minus fn fx less than epsilon. Let's put epsilon by 3. By 3 actually to calculate to get it epsilon. Nothing else. For all n bigger than n naught and for all x in E. So given this is given 1. And secondly, given Fn is continuous, right? On E. Now we have chosen already here for each x naught, so we have chosen an x naught. So this is for each x naught in E for every epsilon greater than 0, there exists delta greater than 0 such that mod of fn x minus fn x naught such that mod of x minus x naught less than delta implies mod of fn x minus fn x naught less than epsilon by 3. Right? We are given this two. Is this clear that we are given this two? Yeah. Let us look at the statement. So fn are continuous function and converges to function f uniformly, right? So this one uniform convergence. And this one continuity. Is this clear?
Yes, sir.
All right. Now we use this two to get this. Well, we need to get a delta, right? So delta will be coming from here. Now we now look at mod of fx minus fx naught. Fix x naught in E is mod of fx minus fnx plus fn x naught minus fnx naught. What did I do? fnx plus fnx minus fnx naught plus fnx naught minus fx naught. All right. So we have added fnx plus fnx minus fnx minus fnx naught plus fnx naught. Now use triangle inequality. Fx minus fnx plus fnx naught fnx minus fnx naught plus fnx naught minus f of x naught. All right. Is this clear? This triangle inequality?
Yes, sir.
Okay. Now see, uniform convergence gives you this is less than epsilon by 3. Where? For all n bigger than n naught. Right? Continuity gives you this one less than epsilon by 3. Where? For mod x minus x naught less than delta. Right? Well, this one you need to intersect with E, of course. We are looking at, say, points only on E. And then again, this will be less than epsilon by 3 because we have used already this one, right? This is in particular true for x naught also. So this is epsilon less than epsilon by 3 again. So what do you get? We get for every epsilon greater than 0, there exists a delta greater than 0 such that mod of x minus x naught less than delta implies mod of fx minus fx naught less than epsilon. All right. See this, but this part has no role in the left hand side. All right. So you can choose n to be particular instead of just for all this inequality. You can choose this one n naught plus 1. N naught plus 1. N naught plus 1. N naught plus 1. Is this clear? So you get only whenever this holds. This part was in the middle, right? So whatever you want, you can choose. That doesn't matter. Is this clear? Is this clear? Any question? Is it what?
Yes, sir, it's clear.
Okay. Yeah, so this is one of the main theorem here. And of course, as you were saying, to check whether something is convergent, uniform or not, this gives an easier one when the limit is continuous. When the limit, I mean, when something is not uniformly continuous, that can be detected by looking at the limit. So note here, if a sequence of function fn converges to a sequence of continuous functions to a discontinuous function, then the convergence cannot be uniform. Any question here? Yeah, I don't want to go beyond this proof. So if you have any question, please now you ask. And try to appreciate this theorem. Or maybe there's one more thing I can say, which is very easy. Test of uniform convergence. Let fn be a sequence of functions on E, which is subset of real number, such that Mn is defined to be supremum of do we need pointwise convergence? Maybe yes. Let's let me check. Yeah, we need a pointwise limit such that Fn converges to F pointwise. Suppose Mn supremum over E mod fnx minus fx. So supremum x belongs to E. Then Fn converges to F. Fn converges to F uniformly if and only if Mn converges to 0 as n tends to infinity. The proof of this one is exercise, because it's nothing but the definition. It's a consequence of the definition. Yeah, any question? Yeah, if there is no question, then we'll meet tomorrow again. All right.
Sir, I had a small doubt.
Yeah, sure. Which one?
So in the proof of the above theorem about yeah, then actually I had this doubt that if the sequence of functions were continuous on E, right?
Right.
Uh, but the delta we chose was then it should also be dependent on n, right?
Right.
But we didn't take that into account.
Delta depends on. Okay, so which one? Right. Delta depend on. See, point is, when you choose n naught plus 1 particularly, right? Of course,
Yes, sir.
delta would have depend on Fn. But now when you choose n naught plus 1, so you, in this case n naught plus 1 thing will come here, right? Delta corresponding to n equal to, so
N
this
naught plus 1.
delta, right? So this delta corresponds to,
So the new delta is of the n naught plus 1 function.
correspond to f of n naught plus, right? Right.
Yes,
So
sir.
this thought is independent. I mean, you can choose anything.
Okay, sir.
You can choose anything which is bigger than n naught, right? And only this is the place from where you are getting delta, right? This is the place where you are getting delta, right?
Yes, sir.
Other thing does not depend on. Other thing has nothing to do with delta. And here we have to working with only one function, not for all n. Then there would have been problem.
Yeah, so that means that any delta which corresponds to n naught plus anything works, right?
I mean, yeah. So if you choose n naught plus m, I mean, you look at correspond to delta corresponding to that. The delta will work.
Okay, sir.
But it is not. It is just thinking of this delta neighborhood. There is nothing, choosing minimum is not required here. Right? So you get a positive delta. Does that answer your question?
Yes, sir.
All right. Yeah, any other doubt? Questions? Okay then. See you later tomorrow.